and we'll start now. So the last class, I guess last classes, my pen's acting up. Of course it does. What we have discussed is the following. What we call mean sampling and the normal approximation to the binomial distribution. So what we sort of did in those classes is we tried to give you an intuitive reason behind the formulas that we're going to use. I noted a few times that this is actually kind of difficult because the math that this is written in is calculus and higher. But that being said, it doesn't mean we can't learn from these things. You know, I use this sort of metaphor, analogy, whatever you want to call it. Like, I mean, you guys drive cars, I drive a car, but I don't know the first thing about building an efficient engine. Pilots fly airplanes. That doesn't mean they have a clue of the physics behind it necessarily. So even though we don't necessarily spit out the details of all the high math, that doesn't mean we can't use these ideas. And so that's what I want to do today. I want to look at homework 9 and I want to go over those problems so that you get an idea of how these formulas that we wrote down can be applied and what kind of questions they can answer. All right, so with that being said, let's do the following. So let's do problems using these ideas. So if I say something at any point that's confusing and you're actually paying attention and following along, please just yell or have me stop, point something out. You know, the idea is for you guys to learn something, even if you think it's not worth learning. I don't know if there's many things that are not worth learning. Some of us adopt that sort of philosophy. Okay, so here we go. We'll call this number 1, but these are the problems straight off of homework 9. So here you go. You copy them down, get it in, get a 10 out of 10. Okay. So we have some, you know, sort of made up scenario here, I guess. Or maybe it's not. Maybe someone does a study and they ask a bunch of people questions and they get answers and they make some, you know, they give us some statistics. So the average electric bill is $72 for a given month. And so what we do is we assume that, let's think realistically. If you've ever paid bills before, you'll realize that something like an electric bill, not everybody gets the same exact bill every month. Your electric bill depends on something. It depends on, for example, how much electricity you consume on any given month. So it's not like we expect everybody in our neighborhood or everybody in our apartment complex or everybody in our county or city to have the same electric bill, at least cost value every month or price. And so if we went and took a bunch of electric bills and got whatever, you know, whatever the monthly bill was, and we computed an average, we could easily do that. And then we have to ask ourselves, how do we think these bills are distributed? And so one common assumption is to assume that it's normal. And so if we assume they're normally distributed, maybe it has some specific standard deviation. So let's go with $6. Now, if you go back and if you read the textbook, which I've encouraged you to do, I put the book up online. We talked about briefly, at least I mentioned it very briefly, and I would encourage you to think about it. So when we say something's normally distributed, we say that these values fall under this sort of bell curve. And we talked about the geometric interpretation of what does standard deviation mean. Well, that just means what percentage of the bills, one way to think about it, is varying from the actual mean. So I would highly encourage you to think about, not just these numbers here, but what's the geometrical interpretation? Leah, not in this scenario, Liam, no. But you could if you wanted.
That would just make it more complicated.
Well, no. I mean, look, but we're just saying people's bills. I mean, so that's a good point. You might say, well, so my neighbors, for example, a couple of them don't have electric bills anymore because they put those solar panels on their house. But they wouldn't be included in this, right? We're only talking about people that receive an electric bill. That's all.
Yeah, but I'm talking about the people that have an electric bill, then they also pay a bit extra to maybe hydro type power.
Right, that doesn't. We're not caring where the money's going. All we care about is what they're paying the electric company every month.
I guess so. That makes sense.
All right, so no matter where the money's going, here's what they're paying. I mean, maybe some of that money they're paying is donated to people, sometimes companies like the gas company, electric bill, they have funds set up for the elderly and those who can't afford, to give them discounts. All right, so let's assume then that this is the case. Now here's the question we want to answer. And there's a key word in this statement, and that's what we really need you to think about. So suppose 15 residents are selected at random. What we want to determine is determine the probability that the mean of the 15 residents So let's be very clear what I mean. Maybe it's not clear when you read the original problem. We want to know what's the probability that's less than $75. So before we do any math, we have to make sure we understand what the question's asking or what the problem is wanting us to do. This problem, first off, let me back up a second. If you read what I'm writing now, it's not the exact same thing that I wrote on the homework. You know, I'm using a little bit different English, but the numbers are the same. And the context is the same. So one of the things you might have going on in your head when you first try to do these is you get confused. There's lots of overwhelming sentences, but there's key words also that should help you to understand what we're trying to gain information about. Notice we say 15 residents are selected. So right there, when we see 15 residents are selected, what that should tell us is that we're trying to gain information about a sample of something. I didn't say, if you look at the previous homework when we did problems that sounded similar to this, we didn't say this group or this sample. We said one thing was selected. And so this is sort of what I was trying to get at last week when I talked about understanding, are we studying one, are we trying to study or gain information on an individual piece of data? Or are we trying to gain information on a sample? And in this particular problem, it's a sample. So once we read the question, perhaps, a few times, we have to ask ourselves, okay, what formula? We know there's two formulas that can help us. And we just have to figure out which formula we're going to use. So we're going to do that in a second. First thing I'm going to do, though, is blow my nose. And I apologize, but... All right, I'm back. Can't breathe. Something's itching me. So, okay. So let me sort of say again in more precise terms what we're getting at here. So here's the solution. So since we're interested in the mean, of a sample, we have to choose which formula are we going to use, and we're going to use the following. So I tried last week to sort of discuss this big guy in the sky, or big girl in the sky, whatever it's called, the central limit theorem. And the central limit theorem gives us theoretical information. And sort of in a class of this level, you just have to trust that this formula is actually in agreement with what we see when we do actual experiments. And so this is the formula we have to use. Again, the key word in this problem is the word mean. And since I'm looking for information about a sample mean, I want to use this formula. So let's also be specific on what we want to compute. So in particular, we want the probability that X is less than $75. So we want to compute this. Right, so if I go to the previous page, that's what we're asked to compute, the probability that the bill is less than $75. So there's some context and there's some things I'm taking for granted here. What am I taking for granted? Well, I'm taking for granted the notion that you understand, okay, what's a random variable? Well, X bar, which is the mean of my samples, my 15 guys, that's a random variable. Why is that a random variable? It's a random variable because I said I selected 15 residents at random. So if I select 15, I'm likely to choose 15 different people than, say, maybe Liam selects. So we can't expect that the mean I get of the 15 to be the same thing as the mean that Liam gets, or the mean that someone else would get. Perhaps, Zach, you go out and collect 15. You're going to get a different mean. So and what we're saying is, since every one of us is likely to get a different mean if we perform the same experiment, that is a random variable. Does anybody have a question at this point? So I guess, I guess we could be a little more specific and say this, X bar. So just like we've done in all the other examples, if we want to answer this question, we have to convert our x's to z's using the above formula. Okay, so let's do that. So what are we after? We're after the probability that X bar is less than 75. Now we have to convert that to z's. So one way to do that, and we've done this two different ways. So one way to do that is to just do the algebra. So again, let me remind you of what I mean by, say, do the algebra. So if I come over here on the side, I know that z is X bar minus mu over sigma over root n. So, well, one thing I can do is I can just plug numbers in and see what happens. So I can say, okay, z is equal to 75, and then our mu is 72. Our sigma was 6, and then this is the square root of 15. So if you go to a calculator, you can compute what this number is. So we'll do that. We'll go to a calculator. Or if you want, you can remember your rules from when you were a kid in middle school about how to divide a fraction by a fraction. Multiply by reciprocals and all that. Okay, either way, you end up getting that z is 1.9, let's say 4. So what that means is that means that the probability that X bar is less than 75 is the same exact thing as the probability that Z is less than 1.94. So this is the important step. We have to go from our X, we have to shift. sort of or transition to the standard normal distribution. Okay, so now it just requires that we go look up this probability, whether we do it in the back of our book, whether we do it using a calculator on the computer. There's plenty of free things that'll do this for you. The one we've been using in this class is calculator.net, but don't forget, we also, I posted one to our Canvas page if you want to use it. So if you compute this probability, you get 0.97381, which of course is approximately 97%. just for completeness, let me draw the geometric intuition behind this while you might ponder if you have a question. So remember where these numbers are coming from. I have this standard normal distribution, this curve. Looks like this. And we have this value z, which is 1.94. And so what's happening now, what we're saying is that the area under the curve up to this point, now this is a sketch, it's not exactly completely accurate. So the area of the red region is 0.97381. Does anybody have a comment, question about this particular problem? And by the way, and I know this is not the easiest to quite grasp, but the idea is that we continue this way forever and ever and ever. This blue curve has what are called asymptotes. You might remember that from a class in college algebra, pre-calculus. And the idea is that that blue curve just keeps getting closer and closer and closer to the x-axis. It never touches, but it keeps getting closer and closer. Again, to fully sort of understand those ideas, you have to take, calculus courses, but hopefully just the intuition is there for this particular set of exercises. Does anybody have a comment, question? As I sniffle and sound all disgusting on the video. All right, let's do the next one. All right, so, oh my God, I'm gonna scroll. So the next example, I'm not going to write all the details down, but let's say so the average cholesterol of a brand of eggs is, let's say, 215 milligrams. Once again, we assume normally distributed. And we'll give you a standard deviation. So the first question you might have is, what is it? Well, if I say assume it is normally distributed, there's only one thing I can possibly be talking about. Am I talking about the price of a car? No. Am I talking about the number of eggs in a dozen? No. The only thing that remotely makes sense that I could be referring to is the amount of cholesterol in an egg. So I asked you two questions here, and the reason I asked you two questions was to help illustrate which formula to use. So if a single egg is chosen, determine the probability its cholesterol content is greater than 220. So that's the first question. And I will completely beat the dead horse on this. Let me underline the key word. Single egg. And then next, if a sample of 25 eggs is selected, determine the probability the sample's mean is greater than 220. So these are two different questions. And we're trying to gain information on two complete different things. In the first part, in part A, we care about one egg. In the second part, we are going to look at a sample of 25 eggs. And if I learn how to write, that would be great. So let's erase if a sample. So it's important that you understand the distinction between part A and B. And let's be completely honest with ourselves here. Most humans are not going to get this the first try, the second try. It's going to take practice to learn this if you want to learn it. It's just the way it is. It's very difficult to learn these types of problems and even more specifically understand these ideas by only trying it for 5 or 10 minutes. And you're not going to learn it by watching me. You're going to have to watch me a few times. You're going to have to go to other resources and watch videos maybe on YouTube and look at examples in the book. It's not easy to do this you can't expect that a normal human brain, you can't expect that you're going to make sense of this in 5 minutes. It's just not going to happen. However, with some practice, you'll soon find that you're capable of understanding it. Okay, so does anybody have a question about how this problem is stated or what we're asking you to do? Yes, no, maybe so. Okay, so let us begin. So let's go to the next page. And let's understand the solution here is going to be depending on how we compute the solution, I should say, is going to depend on which part we're talking about. So the solution. So let's do A first. And so since we're talking about a single egg, you're going to use the original formula. This guy. So we can just, plug these values in now. What was our mean? Well, our mean is, so let's just plug it in. This is X. We're interested in 220. The given mean, our population mean, was 215. I'm sorry, this is not an N. Losing my mind, it's a sigma. And our standard deviation was what? 15. So it turns out here our Z is a third. So what were we interested in? Well, we were interested in the probability that X is greater than 220, which is the same as the probability that Z is greater than a third. And then once again, you have to go look this up. So you have to plug this into your calculator. And when you plug it in, you get what? 0.6305. So the way you can interpret this is there is a 65% chance that if you select a random egg, its cholesterol content is greater than 220 milligrams. Does anybody have a question? All right, so that's the first part. That's part A. Now, part B is asking about a sample in the mean of the sample. So we're mean sampling now. So here, since we're talking about the mean of a sample, we use this formula. So once again, we're interested in 220 minus 215, but now we have to divide by a slightly different number. This becomes 15. And then what is our sample? Our sample is 25. So this becomes 5 over 15 over 5, which you can simplify to 5/3. All right, so what's 5/3? Well, if you do the arithmetic, that's approximately 1 point, so what is 1.666? So just like in the previous problem, we can make the following reasoning. The probability that the mean is greater than 220 is the same as the probability that z is greater than 1.66, let's say 7, whatever. And of course, you go to your calculator to compute this. And if you compute this, you get roughly 95%, or 0.95224. So it's very likely then that if you were to take 25 eggs and compute their mean, it's 95% chance that the mean is greater than 220. Or excuse me, yeah, 220. Any questions about this problem? All right, you don't have questions, let's move to the next type. All right, so the next problem is an example of approximating a normal, excuse me, a binomial probability. So suppose we tell you that n is 400. So we're going to have 400 trials. So let's let's make sure we understand that. Well, let's write it like this. So let's remember what we want to do. We can interpret n as the number of trials. Say I'm going to flip a coin 400 times. Or I am going to take a test with 400 multiple choice questions. I'm either going to pay the loan back or I'm not going to pay the loan back 400 times. And P is the probability of success. And so what we're looking at is we're looking at computing P of X equals 20. And how do we read this? Well, this means the probability of 20 successes out of n equals 400 trials. So by definition, what does it mean by definition? Well, it had this scary formula. The scary formula, by definition, you took this thing, which was 400, choose 20, and then it was 0.05 to the 20th power, and then it was 0.95 to the, what power would that be? Well, that would be 400 minus 20, so that would be 380. And so instead of computing that number, which is often difficult to do, even with basic calculators, you know, you need a little more sophisticated calculator to actually compute this because of the size of those numbers. So the normal approximation says instead use that probability that we're after is approximately this probability. Now, we have to be careful because these things mean two different things. Context is key. So let's be very clear. This is the binomial distribution. This is the normal distribution. You might also say, well, where's that 1/2 coming from? Well, we mentioned this last week. The 1/2 is called a continuity correction. And again, going into what that means requires that you have an understanding between discrete and continuous probability distributions. Now, we've asked you to think about this a few times. I'm not suggesting that it's the easiest to think about. And it's a lot easier to understand the more math you quite or that you get as far as what a continuous function is versus a non-continuous function. So you can spend some time to think about why that 1/2 thing is necessary, or you can just trust that it makes sense and move on. That's up to you. But you have to make that decision how you're going to handle that. Does anybody have a question? All right, so what we want to do is if we want to compute this, then that's what we're going to do. And now we're in a problem that we just solved in the previous two examples, only slightly different. So Okay, so hi, Ricky. Hi, Ricky. Ricky, can you go upstairs? No. Hold on. We got a visitor. She's fine, Aim. All right, so we need to compute the following. So we need to compute this binomial, which is this normal. So we had 20 minus a half, so this is 19.5. And then 20 plus a half, which is 20.5. And now if we want to compute this, we need to convert it to its z's. So once again, we have to do a little either algebra or arithmetic, however you want to do it. So what do you have? You have z is x minus mu over sigma. Now, what are our mu and sigma? Well, don't forget, we mentioned this last week. What is mu? Well, mu is NP, and sigma is the square root of N times P times 1 minus P. So now we have to compute these values. So for example, if N is 400 and P is 0.05, then NP is 20. And then if we want to compute the standard deviation, we have to take the square root of this. Taking the square root of this, you get roughly 4.35. Okay. Ricky, can you take that upstairs? Yeah, take it upstairs, please. Uh-huh. So, once again, we have to do this background work. Does anybody have any questions about this? So, all right, bye, Ricky. Bye, Ricky. All right, so what are these values? Well, if we plug them in, as we said, x we're worried about is this 19. We have to do both of them. We have 19.5, and then we have to do it for 20.5. So if you do the calculation, the first one, if you take 19.5 minus 20, and then you divide by sigma, you get negative 0.1149 is less than z. And then if you now do the other x bound, you get 0.1149 that's positive. And then, of course, if you go to your calculator or the back of your book, wherever you want to go, you get, oh, wrong button. So if you plug this into a calculator, you end up getting what? 0.091476. Which is a little less than what? 1%. I'm sorry, excuse me, 10%. Or 9, I guess a little more than 9% if you want. Does anybody have a question about this? Now, of course, if you have a sophisticated calculator, you could probably compute the actual value. Of what we had on the previous page, or 2 pages ago, this creature, 400 over 20, blah, blah, blah. Does anybody have a question about this? Going once. Going twice. So again, this is an approximation, but it's pretty accurate if you went and did the computation carefully of the binomial. Does anybody have a question, comment, concern? Okay, so that was the first part. The next thing we wanted to compute, which is we've actually already done, we just have to interpret it correctly, is the probability that x is greater than or equal to 20. So the probability that x is greater than or equal to 20 is approximately the normal probability that x is greater than 20 minus a half, which in this case is the probability that x is greater than 19.5. So again, let's be very clear with what probabilities we're talking about. This guy's binomial, and on this side, these are normal. Now, we already did this work to answer the previous question, so we know that this is the same thing as the probability that z, if you go to the previous page, is greater than negative 0.1149. And so if you go to the calculator and answer that, we get the following. Does anybody have a question? Comment, concern? Going once, going twice. All right, so if you finish this out, you get what? Well, we're interested in the probability that z is greater than negative 0.1149, which means that's the area under the curve, and so you get 0.54574. Any questions, comments, concerns? All right, so that's how you do that problem. Now let's give you a hint for the last two because they're exactly the same way of doing it, but you have to set them up properly. So for the fourth one, how do you interpret it correctly? Well, here n is 50 because that's how many questions are on the test. And on each question on the test, you can either get it wrong or correct. And then what's the probability you guess it correct? Well, each question has 5 choices, so you have a 1/5 chance of getting it correct. And what we'd like to compute is we want to compute this. You want to compute the probability that x is greater than or equal to 35. Now, by the binomial distribution, this is really, really, really difficult because you have to do this. You have to compute the probability that x is equal to 35 plus the probability that x is equal to 36. And you have to do this all the way up to the probability that you get all 50 correct. Now, there's a quick way to do that, and there's a not quick way to do it. Either way, yikes. And so it should also be pointed out that these are all binomial probabilities. So I want you to do it that way, suffer through it, and then do it using the approximation. So the probability that x is greater than or equal to 35 can be approximated by the probability that x is greater than 35 minus a half. And so, of course, once again, this is binomial. And this is normal. So you just repeat what we did on the previous problem. And then once you answer that question, you decide if guessing is good or bad. Okay, so that's how you would do that one. If you have a question, please point it out, because the last one is almost identical. You're just changing your probability of success and failure. You just have to set the problem up correct. All right, so for the last one, we're going to sample 150 restaurants. So we're going to take 150 restaurants and we're going to ask, did it succeed or did it fail? Success or failure? So here your N is 150. What is your probability of success after 1 year? Well, your probability of success is 17 out of 100. Or excuse me, that's, okay, this is the probability of failure. So it doesn't matter whether you do failure or success. And so 1 minus P, which would be your success. So if 17 out of 100 fail, how many succeed? Well, 63 will succeed. Or excuse me, 63. 73 will succeed. Oh my God. This is where arithmetic gets us, right? So if 17 fail out of every 100, that means how many have to succeed? Well, do the 100 minus 17 and you get 83 succeed. So the probability of success is 83%. The probability of failure is 17%. And so we want to know which ones are still in business. So we have to make sure we set this up correctly. So we need to approximate we want at least half of them. So we want to approximate this. Half of 100 is 50. So we want to know this creature. So that gets you going. It's a tricky problem, but there's one that it's one that you can definitely get to the bottom of. Does anybody have a question? Okay. Then I will end it there. And again, I hope to see you guys Thursday. If you have any questions, I know some of you have emailed me already. I'm trying to catch up on that. I'll get back to you as soon as I can. But do not hesitate to continually email me. It doesn't make me mad. It just makes me more likely to see them. So, all right. If you guys don't have any questions, we'll end now.